Hi everybody, my name is Clément and I will talk about parenting via model-agnostic reinforcement learning to correct pathological behaviors in data-to-text generation. This work is jointly done with Laure Soulier, Geoffrey Scoutheeten and Patrick Gallinari. The overview of today's talk is really simple. First, I will present the data-to-text task with some examples and talk about the pathologies of DTT, namely omissions and hallucinations, as well as the current limits of existing approaches. Then, I will present the parenting framework we've worked on and the experimental evaluation we've conducted. I will finally conclude with some interesting perspectives about future work. The data-to-text tasks comes from three key facts. First, knowledge and data are often modeled in a structured way, such as key-value pairs. Second, these data are not really usable by humans and need to be synthesized. And finally, communication via text is more effective than via raw data and can lead to a significant improvement on downstream tasks. The DTT pipeline is really simple. There is first a content selection step, then a content ordering step, and finally surface realization where we choose the actual words in our text. There are also the syntax aggregation subtask. Notice at the end of the text it says INLG 2020 and not the full conference name, or data abstraction or interpretation subtask. For instance, this text is written at the future tense because the published date is in the future. In the real life, data-to-text can be quite intimidating, for instance in the financial sector, here with the complex data, which comes from the performances of a financial product of a French bank. The data-to-text community uses simpler datasets such as Wikibio, which pairs the info box of the Wikipedia page with the first sentence of the associated article. Formally, an instance of a data-to-text dataset is comprised of a table T, which is a collection of records which are key-value pairs, a reference text R, which is a sequence of words, and we can include G, which is a generated text by an automatic system. It's all really intuitive. If you look at the figure below, you see that the table is the data in its globality, and each line is a record, where the title of the line is the key and the value is simply the value. The pathologies in DTT can be split in two categories. First, we have omissions. It's expected content that is not found in the generated text. If we look at the figure above, and the reference a soccer player who plays as a forward, the birthplace is missing from this sentence. It's an omission. In contrast, hallucinations are excerpts from the generated text that should not be there and not grounded by the source table. In the generated text, a Utah forward from the national team, the end of the sentence should not be there because it's not supported by the table. Omissions are most likely found in handcrafted datasets which are designed specifically for surface realization and should have a one-to-one alignment between the table and the generated text. In contrast, hallucinations are found in more complex and larger datasets which are gathered from online sources. The root causes of these pathologies come from the training procedure as well as the training data. In other words, garbage in, garbage out. We can look closely at how divergence leads to hallucinations. Divergence are found in training instances. There are fragments from sentences that are true but come from another source than the associated table. The model learns during training time to mimic this behavior and during inference will output true-sounding but still false statements. We call these hallucinations. If garbage in, garbage out, we may be able to clean the datasets by adding or removing records from tables so that we have a perfect source target alignment to ensure that the model don't learn stupid stuff. There are actual work on this, and they have shown that standard neural networks work better on clean data. However, all these works have been done on E2E, which is an easy dataset, only 8 records and no content selection task. Actually, at this INLG conference, Thompson will present the same kind of work on a more complex settings on the RotoWire dataset and shows that additional records work even though we don't obtain a perfect alignment in the end. However, the cleaning procedures are manually tuned for most part, and this can be costly to design once and to redesign for each new task and each new dataset. If we don't want to spend the cost of cleaning the datasets, maybe we can try changing the training procedures, either by adding dedicated neural modules, but those are not compatible with pre-trained models, such as BERT, for instance, or either by changing the loss for something less constraining than the standard cross-entropy loss. However, this change of loss is often done via reinforcement learning using bleu or rouge scores, which heavily impacts the fluency of generated text. With this in mind, we will present our parenting framework. First, a bit of background, the parent metric introduced last year by Dingra et al., which is similar to bleu, but works both on the target and the source table. It evaluates the generated text on precision and recall. If you remember, we have a source table T, a target reference R, and a generated text G. First, the parent precision is the fraction of n-grams from G, which are either found in the reference or in the table. In blue, it's the fraction of n-grams from the generated text that are found in the reference, so it's kind of the same. The recall is more complicated and is the average of a recall and a coverage score, where the recall is the fraction of n-gram from both the reference and the table, which are found in the generated text, and the coverage is simply the fraction of n-grams from the table, which are found in the generated text. Now that we know about parents, we can outline 4 objectives for our framework. First, we need a generic framework to work with any neural models and for both omissions and hallucinations. Second, we need a model trained via this framework to distantiate itself from the reference to stop copying the problematic behaviors from the training data. And third, I realize it's not an objective but much more of a remark, parent is a good proxy for human judgment of a text. And fourth, we need to keep fluency despite our use of parent, which is a discrete metric, as we said before. To answer these 4 objectives, we propose parent, which only changes the loss of a standard DTT pipeline, which this new loss will be using reinforcement learning with a reward based on parent. And to keep fluency, we use a mixed objective loss function so that the new loss is a bit of RL, and a bit of cross entropy. Usually gamma here is quite low in practice. The error training procedure is very simple. You may or may not start with a pre-trained model, and one training step of reinforcement learning starts with generating a candidate sequence Y sampled randomly. So each word, we get the probas learned by the model and sample the words following these probabilities. And then we update the weights of the network depending on the reward of this sentence. In our work, we pre-train the model and we really want to avoid overfitting on easy trained instances, so we use self-critical reinforcement learning. We still generate a candidate sequence YC, sampled randomly, but we also generate a baseline YB with greedy decoding, basically taking always the top probability. The reward of the candidate sequence now depends not only on its parent score, but also on the parent score of the baseline. This will make it so that on easy instances, the baseline will obtain a high parent score, so the global reward for the candidate sequence will be low. And on hard instances, where the baseline parent score will be low, we give the model a chance for a higher reward for good candidate sequences. We evaluate our approach on 2 datasets. The Web-INLG dataset, which is handcrafted and evaluates surface realization. We expect to find omissions there. And the Wikibio dataset, which is built from online sources. And models trained on these datasets tend to hallucinate a lot. To show that our approach works for any model, we experiment with LSTM and with the transformer. We evaluate our approach using bleu and parents, as usual, but also using human evaluation to better measure the subtleties in fluency, factualness, and coverage of the model outputs. We compare our approaches to the state-of-the-art on Web-INLG, which is a graph convolutional network, and to Gardent LSTM, which is a simple implementation of the LSTM, that comes with the dataset. On Wikibio, we will compare our approach to a sequence-to-sequence network with the forced attention module and trained via reinforcement learning. The forced attention is here to improve coverage, while the reinforcement learning using blue is expected to increase factualness, and to a confidence pointer generator network, which has a confidence neural module, which is used to trim off words when it is considered an hallucinated word. The table of results is quite big, so we will proceed step by step. First, at the WebNLG dataset, we can see that training via RL increases most of the performances significantly. And in particular, we can see an improvement on the recall score, which shows that we are dealing with omissions. The gain in performance might be quite small, but it's because WebNLG is already kind of a perfect dataset, so not the most interesting there. In contrast, in Wikibio, we see that we increase both precision and recall, showing that our approach is efficient at handling both omissions and hallucinations. And if we compare with Confident PG obtains a very high parent precision, but at the cost of a very low recall score, contrasting with our approach, which obtains a higher precision score and a much higher recall score. The dedicated module here for factualness, which trims hallucinated words, fails at recall. Comparing with the sequence-to-sequence with forced attention and RL, we see that it's much more balanced with not quite high precision, but still high and higher recall. But our approach overperforms on both precision and recall. And finally, we can conclude that while the dedicated forced attention module is efficient at recall, it's not optimal either in recall or in precision. Finally, we have conducted a human evaluation where we asked participants to score the fluency, factualness, and count the number of realized rows from the table. We see that, as expected, the fluency of the S2S FA-RL model drops dramatically, which is because of the blur reward and the reinforcement learning training procedure, contrasting with our mixed objective procedure, which obtains really fluent outputs. We also see that factualness is very much increased with the parent rewards, contrasting with the blur reward. And regarding coverage, S2S FA-RL obtains better coverage, which is certainly due to the FA module, but we can say that this coverage is higher than the gold score, which is not a good thing, maybe, because we want to aim for human performance and not over human performance. Maybe this model says too much. In conclusion, we have proposed a setting and model agnostic framework, which works both for omission and hallucinations, using self-critical reinforcement learning with a parent-based reward. The results are improved across the board for both the LSTMs family and the transformers family on two different benchmarks, which were WebNLG and Wikibio. For future work, we really want to outline that 72% of factual outputs is not enough for real-life performances. We need close, or maybe we need 100% for real-life applications. And we want to try and work on the word-level approach, where divergences would not be annotated at the instance level, like with the parent reward, but at the word level. I will be available for questions now. Thank you.